Welcome. If you're tracking AI's progress in, fundamental research, we're looking today at what feels like a pretty significant moment. We're discussing AlphaEvolve, this evolutionary coding agent, and specifically it's run through a huge 67 problem mathematical stress test. And this isn't just theory. We're talking constructive problem-solving geometry, combinatorics, analysis, number theory. It feels like AI is moving beyond demos, really getting into the day job of research math. So our goal today is to quickly unpack what this means. What is AlphaEvolve really? How does it work differently? Where did it actually make breakthroughs? And importantly, why do the researchers, folks like Terence are involved, see it as an instrument, not, an oracle about to replace everyone?
Right. And the source material really pushes past that speculative question, can AI do math?
Mm.
The answer seems to be a clear yes. But, and this is the crucial part, only when you structure the problem right. It works brilliantly in a defined lane. Specifically for constructive problems where the answer is something you can build or find, and critically with humans still very much in the loop.
Yeah.
So this analysis is really for researchers, engineers, people who need the practical takeaways now without all the fluff.
Okay, let's start right there. What is AlphaEvolve, technically? Because when people hear AI solves math, they usually think of LLMs trying to prove theorems, right? Like symbolic reasoning. But you're saying that's not what this is.
Exactly. That's the number one thing to get straight. AlphaEvolve is fundamentally a search machine. It writes code, and then it evolves that code. You don't give it a theorem to prove. You give it a score function, something highly measurable. Like, how densely can you pack spheres? What's the lowest constant in this inequality?
Okay, so it needs a number to optimize.
Precisely. It uses a large language model, a state-of-the-art one, to propose mutations to the program code. It literally writes slightly different versions. Then it runs that new code, gets the score, sees if it did better, and iterates, keeping the best programs and evolving them further. Think of it as evolution, but acting on source code that generates mathematical objects, not just tweaking parameters.
So it's treating the whole process like a kind of hyper-optimized engineering challenge. Find the best configuration, find the tightest bound.
You got it. And it's a big step up from earlier work, like FunSearch. AlphaEvolve can evolve whole files of code, sometimes hundreds of lines long, that lets it handle more complexity. And critically, it can optimize for multiple metrics at once. Plus, they ran it for longer on faster hardware. The goal isn't some long, complex proof. It's finding that surprisingly short, maybe elegant bit of code that produces a really efficient, complex mathematical object.
Right, it's pragmatic. It's asking the AI, can you tweak this construction until it beats the current record? It's a pipeline. Propose, test, refine, but at a massive scale. Okay, let's talk about that test then, the gauntlet. 67 problems that sounds incredibly broad. Kakeya sets, autocorrelation. This wasn't just picking easy wins, was it?
Not at all. They're deliberately testing its capacity for constructive exploration across a really wide front of modern mathematics. And importantly, it wasn't just finding things we already knew. It made verifiable improvements, real breakthroughs.
Okay, let's hear about those. What were the big aha moments?
Well, there are three really standout results where it pushed the boundary. First, the kissing numbers problem in 11 dimensions. 100 and $100 roll.
The kissing number. How many spheres can you pack around a central one?
Exactly. Simple concept, but it gets insanely hard in higher dimensions. In 3D, the answer is 12. We know that. But in 11 dimensions, this problem has stumped people for centuries. The best-known lower bound was 592. AlphaEvolve found an explicit configuration that fits 593.
Hang on, just one more sphere. It went from 592 to 593. Why is adding just one sphere considered such a massive deal?
Because the search space in 11 dimensions is just astronomically vast. The degrees of freedom, the ways things can fit together or clash, it's beyond human intuition. For decades, the best anyone could prove or construct was 592. Finding a stable arrangement for one extra sphere means the AI navigated this incredibly complex space and found a loophole, basically, a configuration humans missed.
Okay, that makes sense. It's proof the search is really exploring new territory. What was the second big one?
The second was in analysis and combinatorics. It's called the autocorrelation inequality, specifically problem C6 2 Tallers. This relates to finding sequences with minimal interference patterns, which is important in things like signal processing. The system managed to drive the best-known upper bound down from 1.50992 to less than or equal to 1.5032.
Another concrete improvement.
Yes, but what's maybe even more interesting is how it got there. The agent didn't just find the answer, it learned sophisticated search techniques along the way. It actually evolved to use a Newton-type optimization step. And it independently discovered a strategy the researchers called cubic backtracking.
Wow, so it wasn't just finding the needle, it was inventing a better way to search for the needle.
Pretty much. Learn the kind of search discipline needed for that specific complex landscape.
Incredible. Okay, and the third one, finite field geometry.
Yep, Kakeya sets, specifically in 3D over finite fields, Math BBFP2. The Kakeya problem is about the smallest area you need to rotate a needle 360 degrees. Over finite fields, it's an algebraic version. AlphaEvolve found explicit constructions that tweak the best-known size formula, improving the lower-order terms. Again, detailed, hard-won progress.
This is where it gets really interesting for me based on the material. They talk about generalization from small n, putting the agent in generalizer mode. Brute search is great for finding a filers, but getting the formula for filers that feels like a human insight thing?
Exactly, that's the jump, right? Calculation gives you $5, it goes 402.2. Generalization gives you the code or the formula for $5. They task the agent with writing a single program that could solve a whole family of related problems, aiming for formulas that hold true for any input modulars. And that's usually where brute force just hits a wall. It can find instances, but not the underlying pattern expressed as a formula.
And did it work?
It did. And this led to perhaps the most exciting human-AI collaboration moment. One of the generalized constructions the machine found, this time for Nicodemus, that's another geometric problem, directly sparked a new paper by Terence.
Wow.
Yeah. The machine finds this crisp, verifiable pattern, maybe a complex one. The human expert looks at it, understands the structure behind the pattern, and then elevates it into a formal, provable theorem. Machine finds, human proves.
Okay, but that brings up the trust issue. Reproducibility, the actual model weights, the LLM they use, that's not open source, right?
Yeah.
So how reliable is all this? People are naturally skeptical.
They address this directly, and it's a really crucial distinction. You don't actually need to trust the model. You just need to verify the output. Meaning AlphaEvolve spits out explicit constructions and the code that generates them. If it says it found a 593 sphere packing, it gives you the coordinates. You, or any mathematician, can run the verification code. Check the Kakeya set construction yourself. You don't need to know how the LLM came up with that code. The final mathematical object, the specimen, is right there on the table, independently testable. The LLM is just the tool, like a really advanced microscope used to find it.
Okay, that makes sense. They described a kind of pipeline for this, right? Using the Kakeya example.
Exactly. A really credible loop for discovery. Step 1. AlphaEvolve finds the construction, the raw object. Step 2. A different tool, called DeepThink, analyzes that construction and tries to derive a closed-form size formula and maybe a human-readable proof sketch. Step 3. That argument gets fed to AlphaProof, which attempts to formalize the whole thing in Lean, the proof assistant.
Search, reason, formalize.
Yeah, it's about as audit-friendly as you can get with AI and math right now. But they were also really honest about the limits. It's not magic. The system struggles if the scoring landscape is too rough, too many local optima, or if checking a potential solution takes too long or is prone to errors.
So it needs a well-behaved problem.
It helps. For instance, they got the 3D Kakeya result formalized in Lean. But when they tried it in 4D and 5D, the constructions AlphaEvolve found were so intricate that the automated formal proof just stalled. It became too complex computationally and needed significant human intervention to verify.
So the AI pushes the boundary, but humans are still the ultimate arbiters, especially for complex proofs.
Definitely. It's an aggressive explorer, but we're still the ones drawing the final map and checking the details.
Okay, so let's pivot to the practical side. If you're a researcher, an engineer, working in optimization or a related area, what's the takeaway? How does this change how you might work? The material stresses collaboration.
Absolutely. It's a team sport. The AI isn't running the lab on its own yet. Human input was critical in basically 3 key areas. First, problem formulation. And this might be the hardest part intellectually. You, the human, need to translate your abstract goal, find a tighter bound, into a concrete, computable score function that the AI can actually search effectively.
Building that bridge from theory to computation.
Exactly. That's a human task.
Yeah.
Second, insightful prompting. It's not just setting the goal, but giving little nudges. Remember the cubic backtracking. That emerged after a human simply hinted in the prompt to consider something like a Newton-type step. That small hint unlocked a better search heuristic in the AI.
So you guide its learning process a bit.
You provide a seed idea, and the machine might just run with it in unexpected ways. And the third area is interpretation and generalization. The machine might spit out some incredibly complex thing, that Nicodemus construction with 100 variables. That's the spark. The human expert then steps back, looks at it, and asks, okay, what's the core idea here? How can I simplify this? How do I turn this specific construction into a general theorem or a cleaner result? Machine finds the messy solution. Human finds the elegance and proof.
So the practical advice is, don't expect the AI to do everything. Separate the search from the proof.
Yeah.
Use the AI to find the objects, the configurations, the examples.
Yes. Use it as a superpowered code-writing lab assistant. Let it find those needles in the haystack.
Yeah.
Then you take those needles, the concrete constructions, the code, and feed them into your symbolic tools, your proof assistants, or just your own brain for analysis.
Right. Treat it as a generator of verifiable candidates, not a black box oracle.
Precisely. It's a chain of heuristics and code you can actually look at and test. That workflow fits much better with how science actually progresses, compared to waiting for an AI to hand you a finished theorem.
Okay, so wrapping this up, AlphaEvolve isn't replacing mathematicians. What it is doing is dramatically expanding the search space for mathematical discovery. It runs countless experiments and, crucially, shows it can distill patterns from those experiments into general formulas.
And it gives us concrete things to work with those 593 spheres, that tighter constant. These become the raw material for human analysis and deeper theoretical understanding.
So if your work touches on optimization, finding configurations, constructive problems in geometry or combinatorics,
The message is, this approach is working now. It's delivering quantifiable results, sparking new human-driven theorems. It shows computation can be a genuine partner in discovery.
which leads us to a final thought, a kind of challenge drawn from the material itself. Think about a hard problem in your field, one where you could, at least in principle, define a score. How good is this configuration? How tight is this bound? Could you wire up a search loop? Maybe not as sophisticated as AlphaEvolve, but the principle. And then when the machine inevitably brings back something weird, something unexpected, maybe just slightly better than what's known.
That's your starting point. Don't just dismiss the weird construction because it doesn't look like the textbook answer. Your job, then, is to figure out why it works. Explain it. Simplify it. Turn that computational artifact, that unexpected discovery, into lasting mathematical knowledge. That's where the real synergy happens.